Some of these examples, you can tell, will be really good to go back to when you revisit quantum mechanics again. Let's look at another Mathematica file. Now, at the beginning here, I forgot that I had done assuming in the other one, so this is just a little review of assuming. But for this one, I now want to take advantage of using functions to do a bunch of stuff for the series. So I'm going to make a general function. So the formula for making a function in Mathematica is colon equals. And the other part you want to understand is whenever I use an underscore in Mathematica, I'm declaring something to be a pattern. So we'll use that in some other places when we solve differential equations by substituting in series. We mentioned it very briefly at the beginning of the quarter. But the idea is, the nice thing is, this variable L, I haven't really used up L. L's not assigned to anything. It's just telling Mathematica a pattern's going to occur, and whatever shows up here, you put wherever you see L over here in the function. Whatever shows up here, you put wherever you see f of x, and so on. And now I'm definitely doing these, in terms of the normalization where I'm thinking of this as a vector space. And I've built in my square root of L, though I am doing it from an interval from 0 to 2L. So this is not a function that can arbitrarily pick the interval. And so I give it L, I give it the one I want, and I give it the function, and I get the coefficient, and I can do the sine, the cosine, the zero coefficient, or the exponential. So I can do any of the series that I want to do. Now I want to go through a case, and one thing, watch what I do today, because tomorrow, Thursday, you're going to do sine cubed. But I'm going to do sine to the fifth. So the first thing I want to do is check out the coefficients. Whoops. Oh. And what do we notice about the structure? Which you can cheat and look ahead in the file. But if I look at my sine coefficients, what's something I'm getting? Sine 2n pi is what? 0. Perfect. So I notice if I simplify this or use assumptions doing any of the various things I've had before, I get that all my coefficients are 0. Is that really true? Are there n's in the denominator? What happens when the denominator is 0? It's undefined, 0 over 0. And what, for instance, is sine x over x as x goes to 0? 1. So there's a good chance that at some values of n, this is not 0. In fact, they would be where n is integers that I'm going to use. So the first thing I might do is this. Now, if you notice, I have a power expand simplify. That was left over from when I was doing, I think, sine x to the fourth or something. And then some of the n's are complex numbers. And those you don't have to worry about because they're not integers. They're not where n went to 0. But here are my n's. Now, in doing a sine series, I only have to worry about positive n's. I don't have to worry about the negative ones. So that tells me that for x to the fifth, I do have to worry about it n equals 1, 3, and 5. So let's do those. Notice if I just plug in n equals 3, it tells me, oh, it's no longer 0, now it's 0 over 0. I don't know what to do with that. There's a couple of things you could do. One thing is I could do the limit. So Mathematica, of course, has a limit function, which is what we said, right? When we get 0 over 0, we're really taking the limit as n goes to 0. And I see what it is. I could do that for each of them. But turns out, in this case, if I use my sine coefficient function, it integrates everything fine. And it's really, and I wrote some nice words here, it's basically because of the order that it's doing it. So let's look back at the things that are going wrong here. And if I look back at my sine coefficient function, I am putting in a value for n. So I don't have to assume n's an integer anymore. Right? To get the sign to be 0, I had to assume n was an integer. I am putting in a value of n, and I'm putting it in before I do the integral. So I'm not getting a general formula. It just so happens that the formula written in terms of n was undetermined, but as we saw when we did the limit, the integral is not undetermined. So if I just do it as an integral with a specific value of n, there's no reason for Mathematica at any point to get concerned. It never finds 0 over 0. It just finds the value of the integral. Does that make sense?
And which one didn't have n?
So what happened was, it's the difference between doing it with a general n and trying to get a formula for n versus plugging in a value for n and just doing that integral. The integral of sine 3x times sine x cubed exists, and Mathematica just does it. It doesn't do the formula first and then plug in n, because it doesn't know that there's an n here anymore. There's now a 3. Does that make sense? Every now and then, you know, and this is one of those things with Mathematica, every now and then the order that you do it in doesn't quite do what you want, and you get these things that are indeterminate or 0 or 0 or 0 when they should actually have a value. And then you want to go back. That's why you have to pay attention. You do have to have some idea of what you expect so that you can check some of these numerical things. And notice, I can convince you of that by doing it 2 different ways. I just plug in 3 for my function, sine 3x, and integrate it. So the integral of sine 3x, Mathematica knows what it is. If I integrate sine nx first and then substitute 3 for n, it complains. Make sense? So it's the difference between doing the symbolic integral with any general n and the specific integral with 3. Now, if I want to use the Mathematica Fourier series command, I see indeed I get, notice I'm getting a 5 and a minus 5 with an I and a negative sign between them. So what's that? But what's this going to, if I have i's times e to the i's with a negative sign, is that a sine or a cosine? Sine x is e to the if you are doing Fourier series and Fourier transforms, remembering these 2 formulas is key, because it tells you the connection. A sine, because we're constantly going back between sine, cosine, and exponential transforms when we do this. And the exponentials always come in complex conjugate pairs to be real. And if there's an I and a minus sign, it's a sine. If it's no I and a plus sign, it's a cosine. So when I look at this pairing, notice at first glance, I took a completely real function, sine x to the 5th, and I apparently got a completely imaginary number, because it's I times everything. And then I realized, oh wait, now I've got e to the minus I, e to the I, e to the minus I, e to the minus 3, e to the 3, e to the minus 5I, e to the 5, all with opposite signs. I've got a sine series here. And indeed, if I used my exponential coefficient function, which I created, and do this, I get it out. And that's why with the exponential, you've got to go from minus n to n. If I go from 0 to n, I chop off a whole bunch of the things that make my answer real. And it's that whole fundamental thing of the cosine and the sine being these complex conjugate pairs of e's. So that's a fundamental idea in Fourier series to have. Now, one thing in preparation for Thursday you might want to think about is it obvious why this particular Fourier series is finite and has only x, 3x, and 5x? Because you'll be asked to think about that Thursday for sine cubed. Now, one thing I wanted to highlight real briefly, I kind of had to come up with one because I could actually do this probably in one line if I wanted to. But I wanted an excuse to make a function for you. Because as we do more complicated things, this is a useful thing. Now, writing functions is basically writing programs in Mathematica. The main tool is the concept of a block. And one nice thing in Mathematica, we don't really have global and local variables per se. But we do have it in the following sense. So anything here that goes as an input to my function is, like I said, a pattern matching thing. And so if I use it here, it never gets assigned a value and I don't have to worry about it. But anything else, like at this step where I go norm equals the square root, that defines norm even outside the program, unless I put it in my list of protected variables. So if you've ever done programming with global and local variables, that's the phrasing you would use here. But basically the structure is, it's a function, so you do colon equals. Block tells me everything in here is what I'm going to execute. And then anything here in parentheses are variables that are basically protected. If I'm going to use x or I or common letters that I use outside of this function, I want them in this list. If you use, like I have sum, and I'm using I as my sum, those are automatically ones that don't get a fixed value. So I don't have to list I here, because it's being used in my sum. And all I did here to make it a function is I decided, oh, let's do the normalization as a separate step from the series. Obviously, I could put that integral into here if I wanted to. I don't have to do it as a separate step. But basically, I'm now making something that will do a Fourier series between any two limits, L1 and L2. Okay, assuming that L2 is bigger than L1. That's the only assumption, because I didn't put any absolute values in. So the first thing is I normalize by taking the square root of the integral of 1. And the reason I'm doing 1 here, anyone know why I'm doing 1 here? Well, which Fourier series am I doing? Sine, cosine, or exponential? If I look in here, what are my basics functions? Exponentials. So if I want to consider the normalization, the normalization is n. Well, there's a complex conjugate, so it's e to the plus ix e to the minus ix dx. And what is that? 1. E to the 0, right? Plus ix minus ix is e to the ix minus ix, which is e to the 0, which is 1. So that's why I'm normalizing with 1. And then I make my series, and now I can do, the sine x.